We are live. Alrighty. Thanks everybody for coming out to EthVan tonight. Got a few things coming up. Actually, right after this is Container Brewing for the Bitcoin halving party. So that's on till 10 o'clock tonight. So anybody that's interested will be headed that direction. And then tomorrow is there's a base meetup. I think we'll have details for that in Discord. I think it's also on Luma. I think it's on Luma. So if you search that, we'll put that. I think it's if you're following EthVan as well on X, we've retweeted that, I believe. And then Nouns Run on Saturday. I don't know if Owen's back or not. Is Owen back? Do we know?
Unclear.
Not sure.
Don't know.
Unclear. So not sure about the Nouns Run on Saturday. And then we've got Solana meetup next Wednesday, I think. Yeah, the 24th. They're here, 6 o'clock. So if you're looking to learn about Solana and some other fancy things that are super fast, come check that out on Wednesday. And then we'll be back here for EthVan next week. So, all right. That should be it for this. We do have a POAP for this, so if anybody wants, you scan the POAP afterwards. There's some new folks here, so I'll explain that process. But basically, you're just going to take your phone, watch.
He's doing it.
You put the phone
He's
up,
doing it.
NFC, turn it on, and all of a sudden, ba-doop, look at that. It's going to mint this amazing POAP to commemorate that this event happened. So you just need your ENS or your Ethereum address or whatever. And if you're not yet on chain, like some of the people that we've been chatting with here, you can just put your email address in, and you can deal with it once you get on chain. Anyhow, with that, yeah, Andrew, take us away onto ZK proofs. And if anybody has questions, just raise your hand and we'll get you a mic. And then that way, because we are live. So,
awesome. All right.
Thanks, Andrew.
Yeah, thanks, Tango. Thanks for the introduction. Hi, everyone. Welcome to my presentation. So we're going to learn about zero-knowledge proofs. So a bit about me. My name is Andrew. My background's in software engineering. Worked at Microsoft for 7 years, building Windows 10, Windows 11. 2 years ago, I got into Web3. I'm a builder, founder, CTO. My startup is called Real Finance. We're democratizing Hollywood. We are de-risking film investing and fostering community-driven franchises. So if you are interested in that, talk to me afterwards. You can also find me on X, Farcaster, and Discord. Information's right down there. So I want to start first by just acknowledging zklearning.org. zklearning.org is a MOOC that was given in spring of 2023, presented by the instructors on screen, Dan Bonnet, Shafi Goldwasser, Don Song, Justin Thaler, and Yupeng Zhang. All of the content in this presentation is just a summary of the material in the MOOC. So the MOOC is still available. Lectures, readings, coursework are still there. If you guys want to continue your ZK journey afterwards, I would highly recommend going to zklearning.org. Yeah, I can wear it. Yeah. Is this? Ooh. And then, yeah, from there. And then hello. Like that. Yeah. Yeah, there we go. You want to sound adjust me? All good? Sweet. Okay. Well, the presentations today is going to be split into 3 sections. First, we'll introduce ZK proofs, kind of show you how we go from classical proofs to ZK snarks. Then we'll dive into the details of ZK snarks and show you how to construct one. And then the last section, I'll show you 2 real-world applications of using ZK snarks in blockchain. So this is, ZK is a very kind of like heavy subject. If you guys have any questions throughout this presentation, feel free to just jump in, and we'll kind of do it through that. So with that, let's get started with our first section and introduce ZK proofs. So ZK proofs were first conceived in 1985 by the paper The Knowledge Complexity of Interactive Proof Systems by Shafi Goldwasser, Silvio Macali, and Charles Rakoff. Now, while research has been ongoing for the past 20, 30 years, 40 years now, Jesus, development of ZK proofs have recently exploded due to its application in blockchain. With ZK proof technology, you can outsource computation, you can build trustless bridges, and even do private transactions on a public blockchain. Furthermore, there's a lot of non-blockchain applications of ZK proofs that are being looked at. Finance information, credit risk prediction, criminal justice, healthcare. So for example, in healthcare, With a ZK proof, you could potentially prove to like an insurance company some medical records without actually revealing the patient or their personal details. Or in the case of credit risk prediction, a company can kind of prove to the public or an auditor that they are solvent without actually giving all of the assets and their debt to the auditor. So very interesting stuff going on there. In the field of mathematics and cryptography, there's many types of proofs and proof systems. Each bullet point that you see on screen is its own field of study and is unique. However, ZK proof, the word, is currently a hot buzzword in media. When you see it in the wild, it could refer to any of these ideas. Just be aware that they're not all created equal. In practical blockchain applications, only SNARK, STARK, and their ZK variants are used. So in this next section, I'm going to introduce the classical proof, and then build from classical proofs to interactive proofs, and then up to the SNARK. So let's begin by looking at the classical proof, which is what most people are familiar with. Construction, let me get a laser pointer here. Construction of a classical proof looks like this, right? First you make a claim, and then you define some premises, also known as lemmas or axioms or assumptions. You make some logical statements from those premises, and then you finally end up with a conclusion that either supports or contradicts the claim, and the proof is complete. We can look at the example on the right. So we start with the claim. The square of an odd number is also odd. We'll define a premise. By definition, n is an odd number if it can be expressed as n equals 2k plus 1 for some integer k. And then we do some logical statements, right? There's a bunch of math. And we end up with the conclusion, since 2k squared plus 2k is an integer, n squared is also odd. This supports the claim, and the proof is complete. QED. Moving on, we're going to now kind of go to interactive proofs, or interactive proof systems. So in an interactive proof system, here's the setup. First, you have two entities, a prover and a verifier. You can think of these as just computers or algorithms. Then a claim is given to both the prover and the verifier. The prover will give a proof to the verifier analyzes it, and then will either accept or reject the claim. So looking at the example on the right, on the left here, we have this orange P, the prover entity. On the right, we have a blue V, the verifier entity. And the claim, n is a product of two large primes, is given to both of them. The prover will generate a proof. In this case, it will give the two large primes, P and Q, to the verifier. The verifier will then analyze it. It'll check P and Q are prime. It'll multiply them together, compare it to n, and it will accept if P and Q equal n, and it will reject otherwise. There's two important properties of proof systems. The first is known as completeness, and the second is soundness. These properties help ensure the security and effectiveness of proof systems. The first property, completeness, says that true claims have a proof. That means if the claim is true, then an honest prover will be able to convince the verifier to accept. The second property, soundness, means false claims have no proof. This means that if a claim is false, then there's nothing the prover can do to get the verifier to accept. So in our example, n is a product of two primes, satisfy both of these properties. Completeness is satisfied is because if n is a product of two primes, the prover can always just give those two primes to the verifier will always accept. And then if n is not a product of two primes, there's nothing the prover can do, nothing the prover can give to the verifier to have it accept. Soundness and completeness. Another way to think about it is, completeness is that there can't be any false negatives, and soundness means that there can't be any false positives. So an interesting observation I want to make is that after this interaction, in this example that we had, the verifier actually knows more than it did before the interaction. Specifically, before the interaction, the verifier knew that n is the product of two primes. However, after the interaction, the verifier actually knows what those two primes are. It actually knows P and Q. We want to make this interactive proof zero knowledge. We want to hide P and Q from the verifier. So to do that, we need to introduce two new concepts into the system. The first is non-trivial interaction, which means that rather than having the verifier passively read the proof, it can interact and engage with the prover in some sophisticated way. The second is randomness. It means that the verifier's randomness, you can think of it as it can toss a coin, and that it can err on the side of error and accept or reject with some small probability. So to show this example, I'm going to invite Yoni up, and we'll do a live demonstration since we are live, which is super exciting. Let me close this. And then pull this up. All right, so here's the setup. Let me get those papers. We're going to run through a interactive proof. I am going to be the prover entity. Actually, let's switch sides. Okay. I will be the prover entity, and I'm going to try and prove to him the statement, which is called, this is called the two-color problem. He's the verifier. He is a colorblind verifier. He cannot see color. I am a prover. I can see color, and I want to convince Yoni that this piece of paper has two colors on it. Remember, he can't see color. I'm blinded by the light. All right, there we go. Yeah, there we go. All right. So trivially, I could prove this to him by I could, give this to you and give you a spectrometer. You can kind of analyze the paper, but then he'd be able to know what the two colors are. Alternatively, I can give you my eyeballs, and then you can put your eyeballs or my eyeballs in your head. You can look at it, but again, I've now revealed to him what the two colors are. I want to show you that I can actually prove to him that there are two colors here without actually telling him what the two colors are. So the way we do that is, I'm going to give this paper to you. You're going to hold it green side up, or yes, that side up. Pick a side. All right. He's going to flip a coin. You're going to hit that thing, flip a coin. Just tap. I think you can just tap the screen. And if the coin is heads, he's going to flip the paper upside down. And the coin is tails, he's not going to flip the paper upside down. So he's going to flip a coin. I'm not going to see the coin flip. He's going to do something to the paper. He's going to give it to me. And I'm going to try and guess what the coin flip was. All right? So let's start with this. And then you can flip the coin. You'll do something. And then you'll give it to me. All right. I think that his coin toss was tails because the green's up. Is that correct? Sweet. Let's do it again. All right, I think his coin toss was heads. Was that correct? Yes, it was. Awesome. And let's do it one more time just for, posperity's sake. Not looking, not looking. He does something, maybe he doesn't. Hands it back. Your coin toss is tails. All right, so, if we do this 100 times, I could probably guess the coin toss 100 times correctly, and he can be relatively convinced that, this has two colors. Just to show, for completeness, let's say I'm actually a lying prover. I can't see color, and this paper doesn't actually have two colors, right? Let's do this again, exercise again, where you're going to try and flip a coin and do the paper thing and give it back to me. All right, I think it was heads. Was I right? Oh, I was. All right, 1 out of 1. Let's do it again. I'm going to guess tails. All right, come on, one more time. Let's guess tails again. All right. Let's keep going until I get something. Let's keep going. I'm three for 3. Heads. All right. There you go. You can kind of see, right? So, all right. Thank you for the demonstration. Appreciate your time. Thanks, Yoni. So going back here, we can kind of show, hopefully from that little demonstration, that by having these two new properties, non-trivial interaction, right? He was able to do something and give me challenges, and I was able to respond to those challenges. And Yoni, the verifier, was able to do something random, flip a coin, and err on the side of accept or reject with some small probability. So if we analyze this kind of proof system, if the claim is true, right, that first example where the paper had two colors, I was able to convince him that the claim was true. However, the claim was false. That was the second example, which is the one color piece of paper. I only had a 50% probability of convincing him the claim was true. And in the example we showed, I got 3 out of 3 right. That was pretty good. But you can imagine if we did that interaction 100 times, the probability that I would be able to get all 100 correct is 1/2 to the power of 100, which is a really, really, really small number, right? So this is kind of what we mean by when we say error on the side of probability, where if I can convince Yoni with 100 times, 100 coin tosses, and they're all right, he's pretty sure, 1/1 bajillion% sure that the claim is true. But we do give him a little bit of leeway and say, this is cryptography, this is math. You might be wrong 1 out of the heat death of the universe kind of thing. So, with those 2 new properties, non-trivial interaction and randomness, we can show that after the interaction, after I've convinced the verifier that the claim is true and the page contains 2 colors, the verifier did not learn anything new. Specifically, it did not learn what the 2 colors are. And thus, we've made it 0 knowledge. So, to review, at a high level, interactive proofs look like this. The prover solves a problem and then tells the verifier the answer. They have some kind of conversation, and then the goal of the prover is to convince the verifier that the answer is correct. That's an interactive proof. All interactive proofs have to have these 2 properties: completeness, which means that an honest prover can convince the verifier to accept, and soundness, which means that if the prover is lying, then the verifier will catch him in the lie. With 0 knowledge, optionally, we can actually make any interactive proof 0 knowledge by adding randomness and non-trivial interaction. So we're almost to snarks. Next, we're going to look at the interactive argument of knowledge. 2 more concepts. So an interactive argument is when the interactive is an interactive proof where soundness only holds against polynomial time provers. What that means is like the soundness property, right, which is that false claims have no proof. It's based on cryptographic assumptions, such as you can't reverse a SHA-256 algorithm. So in our current world, this interactive arguments, rather than interactive proof, interactive arguments are acceptable because all of our computers today run in polynomial time. However, just be aware that interactive arguments may not be post-quantum secure, which means that if in the future we have some malicious prover that's a quantum supercomputer, and let's say it can break our hashing algorithm, then it may be able to convince a verifier of a false claim. The second concept is knowledge soundness. So in the past, when we talked about soundness, we meant standard soundness, which means that if the verifier accepts that there exists an answer. Knowledge soundness means that if the verifier accepts, the prover actually knows the answer to the claim. So the difference here between standard and knowledge soundness is a little nuanced, but the main takeaway is that knowledge soundness is a strictly stronger statement than standard soundness. And this is especially important in blockchain applications because we don't want our proof systems to just be like, yes, there exists a proof. We really want to guarantee that the prover actually knows the answer. So in this case, for example, it knows the secret of a wallet, or it knows the private key of a wallet, or it knows the transaction it's trying to prove. So that's just what knowledge soundness means. Finally, we can put it all together and get the 0 knowledge interactive argument of knowledge. We now have a proof system where a prover can convince a verifier with high probability that the prover actually knows the answer to a claim without actually revealing anything about the answer. Hooray. All right, so any questions so far? Take a moment. All good? Sweet. So now that we know what a 0 knowledge interactive argument of knowledge is, let's look at one of the most popular categories of proof systems, ZK snarks. So we'll start by talking about why these proof systems are important. So in 1991, there's a paper published by Babai, Fortnow, Levin, and Seghetti, where it said, in this setup being a proof system, a single reliable PC can monitor the operation of a herd of supercomputers working with unreliable software. Now, back in 1991, we weren't really sure what kind of practical application this had. Fast forward to today, though, we can see now that an L1 blockchain fits the description of a single reliable PC, and GPUs fit the description of supercomputers. So we can kind of update this statement and say, with these proof systems, an L1 blockchain can monitor and verify the operations of a herd of untrusted GPUs. This is exactly what we're looking for in like a ZK rollup type of scenario. So today, this talk is going to be focused on snarks. But I want to note that there's a lot of research going on about other zero-knowledge proof systems, such as snargs, bulletproofs, and especially Starks, very popular today. The industry is still experimenting with and figuring out the trade-offs between these different proof systems, and new ones are being discovered every day. It's an active and ongoing area of research and development. So with that being said, let's define SNARK, which stands for Succinct, Non-Interactive Argument of Knowledge. So SNARK is a category of proof systems with the following properties. First, it is succinct. That means the proof size is short and it's fast to verify. It's non-interactive, which means that every verifier can independently verify the claim without talking to the prover. It's an argument of knowledge, which means that the prover knows the information and there's a high probability that the claim is true based on cryptographic assumptions, that argument part. It's not a proof, it's an argument because we're basing on cryptographic assumptions. And then optionally, we can make any snark zero knowledge by applying the randomness and non-trivial interaction methodology that we just showed. So I want to emphasize that the main advantage of snarks and the reason for their popularity is the succinctness property. Succinctness makes the proof size small, or what that means is that the amount of data that you need to give to the verifier is very small, and also makes the proof quick to verify. This is super important. For example, if you want to build a ZK rollup, well, Ethereum transactions have a maximum limit on how much data, the maximum size of the call data or maximum size of the blob. So you can't actually pass an infinite number of data. You can only pass a very small amount. And there's a gas limit, and that means that there's a limit to how much computation, how much work the verifier can do before it ends. So it's really important that in any kind of proof system we build in blockchain, that it's very succinct. So to construct a snark, you use the following two components. First is an interactive oracle proof, or IOP. This is the protocol that the prover and verifier use to talk to each other. Second, you take a commitment scheme, which is an algorithm that condenses the IOP and makes it succinct and zero knowledge. And then you can take any interactive protocol or interactive proof system and make it non-interactive by applying the Fiat-Shamir transform. So let's look at these individually. We'll start with the IOP. Oh, Christian. Yes, sir.
Syncness, like, oh, there we go. Like, is there how can we quantify if something is succinct or not? Like, how do you determine that, or is it just like arbitrary?
There are very mathematical kind of formulas or rules for what is succinctness. It really ultimately depends on the system you're using. So in Ethereum, for example, you have a limit of 24 kilobytes as the call data. So by succinctness there, we mean it needs to be under 24 KB. So we have that upper limit. You could imagine another proof system where maybe it's not 24, it's 50 kilobytes or a gigabyte. Ultimately, what succinct means is, I guess like at a high level, succinct just means that the proof size is smaller than the trivial answer. So in the example where like n is the product of two primes, right? The trivial solution is I give p and q. I give two numbers to the verifier. To make it succinct, I just need to make sure that the data I give is less than those two numbers. So it can only be one number, or it can only be something that's smaller than that, right? So succinct, I think, at a baseline is just smaller than giving the trivial answer, which is just the raw, proof, the raw information. In practice, though, succinctness kind of varies depending on exactly what application you're trying to go for.
Got it. Thank you.
Yeah. So we're diving into the first part of a snark, which is the IOP, interactive oracle proof. An interactive oracle proof is a system of constraints or a system of equations. So think of it as a set of equations that can be proved and verified. The system of constraints is the language of the proof system. These constraints are implemented as arithmetic circuits, A popular format of an arithmetic circuit is called R1CS, or rank 1 constraint system. And the circuits define what type of statements are possible. There's some common programming languages down here. If you want to implement arithmetic circuit, you can do it with a hardware description language, an HDL, most popular one being CIRCOM. This is essentially the same as writing assembly code in traditional computing. You can also build them in, what we call like high-level libraries. So you can use a language like Rust, C++, or Go, which everyone's familiar with. You can use their cool high-level language features like data structures and loops. The issue is that because you're using a library, it compiles down. The circuit you get at the end of the day is a bit larger and less efficient than if you were to do it with CIRCOM. And then there's kind of this in-between, which is a DSL, or domain-specific language, Socrates, Cairo, Noir. So these are languages that have high-level language features like data structures and loops, but since they're optimized for arithmetic circuits, they compile down to relatively efficient circuits. So the next component of a SNARK is the commitment scheme. A commitment scheme is essentially an algorithm that takes an IOP, and IOP measures a set of equations, and makes it and condenses it down to something that is short and quick to verify. This act of condensing the IOP is known as a pre-processing step or a setup step. Commitment schemes are necessary because they take the IOP and makes it succinct, and optionally zero knowledge if you want that. In practice, a commitment scheme, you can just think of it as a hashing algorithm. So the same way you can take like a really big file and hash it down to a smaller chunk of bits, you can do the same thing with equations, systems of equations. You can hash an equation and make it smaller than the original size. So there's two broad categories of commitment schemes. The first is a trusted setup commitment scheme. The word it's called a trusted setup is because there is a magic number that is used as part of the setup step. This magic number needs to be destroyed and forgotten after its use, because if the magic number gets leaked, then a lying prover can actually prove a false claim. The most popular example of a trusted setup is KZG. KZG was used for Ethereum's proto-danksharding feature. The summoning ceremony, where there's a few months where anyone can kind of join and run some code, that was a way to kind of create and destroy the magic number in a decentralized way. So the idea there was we need to create a magic number. Whenever your computer joins this summoning ceremony, it might just create a random number and add it to the magic number list, and then it'll do some math, and then afterwards your computer will destroy that number. And as long as one computer actually destroys the number after it's being used, then no one can figure out what the magic number is, and then we can kind of say it's okay. The second type of commitment schemes is transparent setups. They're transparent because they don't require a magic number, they don't require destroying a magic number, and the setup can be done transparently and out in the open while still maintaining its security. The trade-off between trusted and transparent setups is ultimately how small and how fast the resulting snark will be. You'll see in a few slides that by using a trusted setup, the resulting snark is actually orders of magnitude more efficient than using a transparent one. So finally, to make any interactive protocol non-interactive, we can apply what is called the Fiat-Shamir transform. So instead of, in the original public coin interactive protocol scenario, the verifier flipping a coin to create randomness, the prover can actually generate randomness themselves using a hashing function. So if we look at this one on the left, this was the example that we had. Prover sent a message over to the verifier flipped a coin, sent a challenge back, it responded, repeat, 100 times. By applying Fiat-Shamir, what we can do instead is that the prover can take the message, and then it can hash it. And then that hash will generate some random enough information that it can use as a challenge. And then it'll take that hash and say, okay, that's the challenge, and then it'll generate a response. And then it'll hash that response and use that hash as the next challenge and do that 100 times. And then at the very end, the prover can send the original message, all 100 challenges, and all 100 responses to the verifier, and the verifier can independently verify that it's all good. You can kind of think of in our paper example, maybe if you could hash the paper and get a random number out, if the number was even, that's heads. If the number was odd, that could be tails, right? So you can kind of imagine if I can just hash it 100 times, I get 100 random numbers, and that is pretty much as good as flipping a coin for the verifier. So by applying the Fiat-Shamir transform, we can make any interactive protocol non-interactive, and this is really useful in blockchains because it means that it allows us to prove a claim to a lot of different people without having to talk directly to each of them, which is exactly what we want for decentralized blockchains. So let's put it all together. To build a snark, first, the proven verifier will agree on a system of constraints. This is known as the IOP, or Interactive Oracle Proof. The IOP is pre-processed, or it goes through a setup step where it gets condensed down by using a commitment scheme. You can remove interaction by applying the Fiat-Shamir transform, and then you end up with the snark. And then with the snark, you can apply the common transformations with the randomness and the non-trivial interaction to make it zero knowledge. Cool, let's take a look at some popular commitment schemes and their performance trade-offs. So the first most popular commitment scheme is KZG. It is a trusted setup. And you can see the benefit is the proof size and the verifier size is constant. So O of 1 means that no matter how big your problem is, no matter how big whatever you're trying to prove, the resulting size and speed to verify it is the same. And that's great. It means that if you're trying to prove one question or 1,000 questions or 1,000,000 questions, doesn't matter how complicated it is, it's always the exact same size, proof, and speed. Very crazy, very cool. The other examples, Bulletproof's, Hijack, Story, and Darks, are transparent setups. They don't require a magic number, which is really cool. However, you can kind of see that the proof size and verifier speed is a lot worse. So, if D is the length of the data that you're trying to prove, well, the proof size for Bulletproofs is log D. It's square root of D for Hydrax, which is just not as good as constant size. It should also be noted that not every commitment scheme is appropriate for every use case. In general, common factors when looking at commitment schemes are what is their efficiency, the proof size, the setup requirements, is it trusted or not, and what kind of crypto primitive, what kind of security model it has, and whether or not it's actually applicable to the math questions that you're trying to prove. You can kind of sort of plug and play different IOPs and commitment schemes together and create different snark systems. So here's an example where I take the Plonk IOP, that's the Plonk IOP, and I can apply the KZG commitment scheme, and I get Aztec and Jellyfish. If I take the Plonk IOP and apply Bulletproofs, I get Halo 2. If I apply Fry to it, I get Plonky 2. Finally, let's just do a quick comparison of some popular ZK proof systems. Groth16, Plonk Marlin are both snarks, and they both use a trusted setup. And you can kind of see proof size is constant, verifier time is constant as well. Bulletproofs and Starks are transparent proof systems. They have trade-offs in that the proof size and verifier time is worse than the trusted one, but Starks are post-quantum secure, which is why they're super cool. So that's a really cool thing. So we're on to the last section here. Now that we know what snarks are, we can actually see two real-world applications of them. So in our first example, we'll look at ZK rollups, a layer 1 scaling solution. So in this picture, we have a traditional blockchain. You have a network of computers or nodes, and they talk to each other. Users will send transactions to one of the nodes. They get bundled up into a block. The block gets proposed, gets sent around. Everyone gets to, verify the block. And then if consensus is reached, the block gets added to the blockchain, and the process repeats. So the benefits of this process is that it's very secure, it's very decentralized. However, it's very expensive and slow to do. ZK rollups attempts to solve this using a ZK proof system. So with ZK rollups, users will submit transactions to a centralized prover. This prover can process the transactions way quicker than on the original blockchain. The prover then generates a proof that says what the final result of all of the transactions are, and it will submit that proof to the L1 blockchain, saying this is what you should do. On the L1 blockchain, the nodes can all independently verify the proof succinctly and without interaction, and the soundness property guarantees that a lying prover will get caught and their proof will get rejected. So by using this system, we can significantly increase the throughput of transactions while still maintaining all the security and decentralization of the original blockchain. Examples of projects doing this are ZK Sync Era, Scroll, Aztec, and Linea. The second example we'll look at are ZK bridges, a trustless way to communicate between blockchains. So a traditional bridge works by having some intermediary. It'll read some data from the sender blockchain. Maybe this will be like, user deposit 100 ETH into a bridge contract. And then it will communicate that over to the receiver chain. And it'll tell the receiver chain, hey, go mint 100 ETH to this user. These intermediaries today, some popular ones are side chains like Poly Network and Axelar, committees like Wormhole and Ronin, and Oracles as layer 0. Each of these have their own trust assumptions that they make in order to ensure the correctness correctness of the messages. We've seen numerous instances in the past where these trust assumptions are broken. For example, having the private keys of a committee member stolen, resulting in millions of dollars lost and exploited. So with ZK proof systems, we can create a prover verifier protocol where the centralized prover can read the two most recent blocks of the previous block of the sender blockchain. It'll then generate a proof saying, between block height H, block height T and T plus 1, 100 ETH got minted, and it'll generate a proof and submit that proof on chain to the receiver chain. The receiving chain smart contract can verify that proof, and it can do it quickly, succinctly, and then it can go and do whatever it thinks it needs to do. So, for example, a prover can claim that 100 ETH was minted or deposited between these two blocks. It'll generate a proof that contains the state change between these two blocks, submit to the receiver chain. The receiving chain can verify that, yep, that was a good proof, and then mint the 100 ETH. The benefit of this system over the previous or traditional intermediaries is that it replaces trust assumptions with cryptographic soundness. You can also have very efficient on-chain verification because of the succinctness property of snarks. And we can onboard provers in a permissionless and decentralized way because the soundness property of snarks ensures that lying provers will get caught and rejected, so we don't actually need to trust the provers that are in this network. So to kind of wrap things up, there's a lot of cool ZK stuff happening here in Vancouver. I wanted to give a shout out to the ZK study group, bi-weekly study group that happens here in Decontrol. ZK Cross is an app-specific roll-up kit that helps developers quickly create ZK provable applications. You can check out their GitHub. Contact ZP at zkcross.org to learn more. Personae is the internet's new identity system. They're focused on making your on-chain reputation useful. You can check out their website, cred with 3ds.xyz. It uses ZK cryptography to prove your reputation without revealing your wallet address. Contact Dan on Farcaster for more. And shout out to Linea. They are a Ethereum L2 ZK rollup being built by Consensus. So thank you again to zklearning.org for all the content in here. Special thanks to Francisco Ignacio and Danny Villardel for the feedback on this slide. And that's it. Thanks, everyone. Cool. Any questions? No questions. All right. I hope you learned a lot.
Well, I was going to add, so just going back to like ZK snarks versus starks.
Yeah.
What was kind of like the main difference between the two? Because we always see Stark versus Snark, and
yes. So what does Stark stand for? Succinct, transparent argument of knowledge, something like that.
Okay.
So I think Starks are a completely different protocol, right? They're not built by the same IOP commitment scheme setup that Snarks are. They have their own way of doing things, right? the real benefit there, I think they were created by the Risk Zero team. I think they're
Right.
the ones that kind of pioneered it. I think the main benefit, if we kind of go back to the slide that compared, here, this one. Starks have a transparent setup. They are universal. They're plausibly post-quantum secure. I think this is the kind of the main thing, the main takeaway. Starks are, right, so taking a step back, right, there's a lot of academic research that happened about proof systems for the past like 40 years. And we're like, wow, cool, a lot of cool math happening. But only recently did we actually start like writing code and implementing this and putting this into use. So there's a lot of kind of development happening about like, well, mathematically this works, but let's see if it actually works in implementation. Does it actually work to, Ethereum has very unique requirements. There's a bunch of things that it does. How do you actually quantify the things that Ethereum blockchains do mathematically and then be able to like prove and verify against it, right? Very kind of like weird questions to answer. So there's a lot of development happening, a lot of really smart people trying to figure out the best way to kind of build these proof systems. Starks are just a different category of proof systems that are not really any better or worse in any kind of like objective way. We can just kind of say that there are some properties that may be beneficial to you. So that's what Starks are.
Okay, cool. Yeah, so not a huge, we're still doing ZK. It's still like just using a different style.
Exactly, yeah.
Okay.
It's just, right, kind of going back to, maybe easier if I do that. Going back to like one of the first slides here, right? There's a lot of like the category of proof systems is quite large, right? So interactive proofs, proof knowledge, in non-interactive arguments, snarks, and Stark here. Scalable, transparent argument of knowledge, right? It's just, there's a bunch of different mathematical properties that each of these kind of have. And we as an industry are still trying to find what is the best one for blockchain. And maybe not even blockchain, if you're trying to prove zero knowledge for identity, or you're trying to do some of the other things where you're trying to prove health records, or you're trying to prove solvency of a company. Not every single, proof system just kind of works, one size fit all. So Starks is just another cool area of research happening, all
Got
kind
it.
of trying to solve the same problem.
Perfect. Thank you.
You gave a non-blockchain example. I think it was like criminal justice, if I remember correctly. Yeah, just curious what that looks like.
So the idea of criminal justice is today, if you're in a courtroom, right, and you want to prove to the prosecutor that this person did something or wasn't doing something, right, you kind of have to just be like, here's the person, and they did a thing. Here's the video evidence showing it, right? The idea with zero knowledge is like, what if the person's a child, or what if this like thing that they're doing is not something we want public, right? Can we prove to the prosecutor or the defendant that like my claim, this child was not at the scene of the crime, or this child was whatever, they did do this thing, without actually revealing the actual information, the actual details, without actually showing the video, right? So kind of going back to like the idea of zero knowledge proofs is how do you prove a claim without giving revealing the answer to it. There's a lot of, you can kind of think philosophically, a lot of really cool applications of it. I think the interest is there, but again, it's really hard to quantify. Like, you can quantify like, is this transaction signed correctly? Because it's kind of all math. How do you quantify if a child was at the scene of a crime, right? I think the industry's kind of still figuring out exactly what that looks like, but the idea is at least be able to show this information, prove to the defendant in a way that doesn't reveal the information of the person that you're trying to hide.
Cool, thank you.
Yeah.
We've got a question coming in from online from our homie Sturkey. He's saying, do ZK proofs remove the ability for auditors to verify what they're interacting with? How can we know if someone has broken a DApp if it's private?
Yeah, that's a good question. So I think this all kind of comes back to like, there is the academic kind of like philosophical research of ZK proofs, which is just like, here's a bunch of math equations. We can kind of prove mathematically about the validity of the equation stuff, right? And then you take that math and you put it into practice. and then you kind of hit into a lot of these kind of corner cases, right? So with the question of like, yes, with the ZK proof system, a DApp might prove that it did a bunch of transactions but not actually give you the information. How can you trust that? That is kind of outside of the very narrow scope of the ZK proof math, in the same way as like, when you get audited by the IRS or by the CRA, how do you prove that you're actually giving real documents or that the audit is actually correct, right? Kind of in general, how can you be sure that the company that's being audited is actually being truthful? There's a little bit of like a social human kind of like, best effort kind of thing, an agreement that we're going to give you the documents. If you don't, we'll, send you to jail, and that threat of jail is enough. But obviously it's not perfect. I think in the world of ZK, the kind of lowest level is like, can we mathematically, as a DApp, prove with zero knowledge the validity of some claim? And then there's kind of like the second order of like, well, like we're not actually all just robots doing math here. There's like actual human-y stuff happening. How do we translate the very kind of like ambiguous human nature-y sort of stuff that we're doing in mathematical terms? And there's definitely a little bit of a gap there. So to directly answer, I'd say that like, you just need like, who is watching the watchers in the same sense. We do need to have additional, like ZK proofs is not like a panacea, one size fit all. It doesn't just immediately solve all the problems. There's definitely an assumption of once you enter the system that like, is the data you're even bringing in, is that valid? Is the data coming out right? You have a ZK proof, and the person that's giving you the proof or the validator is like lying and like, being distrustful. How can you actually ensure that doesn't happen? But that's kind of like a second order of magnitude or second level of concerns, where this talk and specifically the ZK proof math is really just about like mathematically what are we doing. So that's probably the best answer I have.
Awesome, thank you. Anybody else? Questions?
I'm gonna, since we're on this slide, talk a bit about this fighting disinformation. The C2PA is actually really interesting. I don't remember what it stands for, but the idea here is like, remember when like Ukraine started happening and like there was pictures and videos coming out and people were like, oh, that picture's actually taken like 2 years ago at like this previous thing. So it's trying to fight that, where you can think of every camera inside the camera in the like motherboard of the CPU. Whenever you take a picture, it will like take the time and the place and that information and essentially like embed it into the image. And then whenever you take that image and you put it into Photoshop, wherever you do some editing, that Photoshop software will maintain that proof in there. So then like, it goes to Photoshop and then it gets sent over email to CNN, and CNN shows it. CNN can then like just look at that kind of like watermark and be able to trust that it was taken in the right place. And where the zero knowledge comes in, which is really interesting, is like, well, I take a picture, but I just want one person, so I crop it. How do you ensure that like the watermark of this whole image is maintained in that one cropped image? Well, what if you have the original image and it has a watermark on it, and then when you open it up in Photoshop and you do the cropping, Photoshop then creates a zero knowledge proof. It says, hey, I can prove that this watermark, that I cropped it, that I took the original image, I cropped it, and here's the watermark. I take all the information, I ZK it, and I come out with a very succinct proof, and I put that proof in the cropped version. And now, when you're CNN, you can just verify, hey, you don't need to know what operation, you don't need to know if it was cropped or resized or whatever. You don't need to know what the original watermark is, but you can still verifiably prove that like this is an original image and it was actually taken at wherever it was claiming to be taken at. So that's kind of, I think, one of the more practical or more like close to production ready implementations of ZK proofs outside of like blockchain and math world. So very cool.
Yeah, cool
stuff there.
Any last questions? All right.
Cool. Well, thanks everyone for coming today.
Yeah, wicked deal.
Hooray.
All right. If you don't mind, please fold up your chairs if you can, and we'll tuck them away. And then if you haven't already, mint your PO app, please.
Yeah, and
do
one
that.
last reminder, this presentation PowerPoint is all online on YouTube and OneDrive already, so just look at the meeting invite or whatever, and you can find a copy there, a version of the presentation there.
Perfect. Alrighty. Thanks, everybody. See you all next week.